Today's topic in the fall workshop series offered by Pentair is designing a water softening system. So this is a basic introduction to cation exchange system specification. Notice we're just sticking right with cation exchange. We're not doing deionization, none of the other rabbit holes we could go down just from the start. So there are 5 simple steps to select water softeners. The beginning of system design. And I say that a bit facetiously because there's a lot of tangents we could go down. But the basics are, especially on municipal water, we need to test the water hardness, understand what the water hardness is, and maybe the iron content. We're not going to do a full water analysis in this discussion. Why? Too many variables there to get this done in a period of time. We need to understand the pipe size coming into the building, determines flow rate, determine daily water use by that customer, and then calculate the volume of resin required to treat that water, and then choose a valve and tank size based on our customer's needs. Seems rather simple. Well, this is a bit like Alice going down the rabbit hole. Looked like a simple choice to chase the rabbit, but it goes a lot of different places. So that's where we're at. Well, first thing we want to do is understand the capacity that we're going to need for our softener. That's going to be based on our water hardness, okay? And what we're going to do is we're going to take the water hardness in grains per gallon. I'm staying out of the metric system for this discussion because that requires a full understanding of everything in the water to achieve that, okay? That's why we're still dealing with grains per gallon a lot in this industry, all right? So we're going to take grains per gallon times approximate daily water use. That will equal capacities required in grains per day. Okay, how much water am I using and how many grains of hardness do I need to remove from that water in a given time frame in 24 hours? Well, 1 grain per gallon is equal to 17.1 parts per million or milligrams per liter, their equivalent units. So 500 ppm is equal to 29.24 grains per gallon. So just some simple examples there. Don't ever mix English and metric units in calculations. They do not play well together. Here's the first caveat. Capacity is variable. You can set capacity via salt dosage. The theoretical amount a resin can exchange is not the same as real world application. A resin per cubic foot typically can do up to 38 to 40,000 grains per gallon in a laboratory setting. Our equipment is never going into a laboratory setting for test purposes. It may go into a lab for making water, but it's still dealing with real world water and more variables than just hardness, okay? That's what those charts are all based on, those loads, just hardness exchange. Nothing else. If you have iron in the water, up to 5 ppm, that's where we really want to draw the line at using water softeners, traditional resins, to do iron treatment unless you're buying special products for that. You're going to want to do iron pre-treatment ahead of a standard cation exchange resin. Between 2 and 5 grains per gallon of hardness per ppm. That's the fudge factor. You're going to add that to your total. So 5 ppm of iron is factored into the hardness at an additional 10 to 25 grains per gallon, depending upon your water chemistry. We're not going to go down that rabbit hole yet. Just some background information. So you're going to be approximating some of this information if you don't have it. That's where this gets wonky. So understand, let's just stick with hardness. That's the only thing we're going to deal with today. All right? So we're going to have a residential case and a simple commercial case, single tank systems, just to keep this straightforward. we're going to have a hardness test at 171 ppm. Same water supply, same town. This equates to 10 grains per gallon in both scenarios. Now it's down to water use. A family of 4 at 70 gallons per day is 280 gallons per day. 280 gallons per day times 10 grains per gallon, 2,800 grains of hardness to be treated. Notice I'm using very, very simple numbers here for examples. This gets a little bit messier as we get odd numbers here. But I digress. 2,800 grains of hardness to be treated daily by the customer's water demand. Okay, this is getting us in the ballpark of what we need to do. On the commercial side, the business is using 5,000 gallons a day. Not a big business. This is like, you're a small restaurant, a hair salon, something like that. This isn't a big building here. 5,000 gallons a day times 10 grains per gallon, 50,000 grains of hardness to be treated. That's every day. So we know the daily capacity required by whatever system we select. So here's the first snagging point when it comes to designing a system. The capacity of a resin is determined by the salt dose we are going to regenerate at. Okay, the most grains of regeneration per pound of salt occurs at 3 pounds of salt per cubic foot of resin. This isn't the most water efficient selection. Okay, we get a decreasing return on efficiency as we add salt. But notice here the line is fairly linear until we get to about 10 pounds of salt and it flattens off. So intuitively from this curve, you can see, wait, where this curve starts to break and flatten out, that's where I want to really kind of stop my choice unless chemistry dictates I have to go here, okay? And that is going to be at about 10 pounds per cubic foot of salt. This gives us 27,000 grains recovered out of that 1 cubic foot, which has a theoretical capacity to do about 38. We can't get there practically in real world. It's not cost effective. Lots of reasons for that. Or we can go salt efficient where we get 15,000. But notice how it drops off in recovery as we add pounds of salt. Okay, diminishing returns here. So this is what that looks like visually from a fully regenerated bed, 15,000 grains with 3 pounds of salt, lots of stuff that isn't used. At 24,000 grains at 8 pounds, we're down here, and 18 pounds of salt at 32 grains. That's a significant decrease or increase in salt. 6 times the amount of salt to get approximately twice the amount of capacity out. So there's some efficiency calculations we need to do in the future to really tweak our systems. We're not going to do that today. So any valve we have can be programmed or set up to get those sorts of efficiencies out based on how we design them. It's part of this discussion this morning a little bit. So resin capacity at different salt dosage. What does this look like? In this residential case, at 2,800 grains to be treated daily at 3 pounds of salt per cubic foot, I'm going to take that number of 15,000 grains from that 3 pounds of salt per cubic foot, divide my treatment required per day, and that's going to give me my cubic feet required to treat this amount of hardness in a given day. So I need 0.2 cubic feet resin required. Well, 0.2 cubic feet of resin really doesn't have the capacity to meet any of my flow demands. right? This is just a theoretical amount. I'm going to go with a cubic foot softener here. Why? Because I got to buy my resin in a cubic foot bag. I'm going to select a cubic foot softener here. Well, that means that softener is going to regenerate once every 5 days in this scenario at 3 pounds of salt. I can deal with that. That's pretty cool. Now, at 10 pounds of salt, I need 1/10 of a cubic foot to meet that demand because I'm getting 27,000 grains back, right? Well, 1 cubic foot softener in that same scenario is every 10 days. Why? Basically, because I'm limited to buying a cubic foot of resin to put in my tank. So a half cubic foot softener would regenerate every 5 days. Okay, that would be just based on capacity required to treat. In the commercial situation, 50,000 grains a day to be treated at 3 pounds of salt, a little bit of math, we're going to get 3.5 cubic feet of resin, or 7 cubic feet if I wanted to keep it a whole number for every other day runs at 3 pounds of salt. But at 10 pounds of salt, that works out to 4 cubic feet every 2 days a run at 10 pounds per cubic feet. We've almost cut the amount of resin in half and shrunk the tank size by adding more resin. So lots of ways to tweak how often we run. Okay, but this is how we get to the capacity of our tank. So when you're designing a system, your salt dose plays a critical role to the capacity. In residential situations, we pretty much keep the cubic foot size softener in most applications the same and adjust the salt dose. Here, we're going to be adjusting resin size, resin amount to affect the results as well. So choice of salt dose greatly impacts the size of the system. Understand the efficiencies you're designing around and impacts they're going to have. So if we start off with designing around this criteria, we're going to be using a lot more resin. So we know how much resin, but what about flow? That was that 400-pound gorilla in the room that we haven't even scratched, right? You know, that amount of resin can treat that amount of hardness in a given day. But what about the reality of pushing water through it? And how much water is my customer actually using? How quickly flow? So suggest always going to your OEM spec sheets. Some of these companies put out some incredible data that is very, very useful. And this is one resin manufacturer's spec sheet. This is just cut and pasted off their sheet. Flow rate, service flow rate per cubic foot of resin, 1 to 5 GPM per cubic foot. Wow, that's pretty low on the one side. Most of us are probably going to go, okay, let's use this 5 GPM number. Okay, why? Because 5 GPM in a cubic foot of resin, that may work for a lot of residential applications, but we need to understand the environment we're putting that in. And we'll get into that in a minute, why that's critical to understand. We use that 5 GPM number, okay? It limits the size of the system, helps get us smaller packages, but there's impacts from it. Now, this is another OEM's information from another OEM's, kind of digests everything they wrote in a 12-page guide down to a couple charts. So here's service flow rate in gallons per minute per cubic foot. They also do it in the metric bed volumes per hour. You can see here at 5 GPM, we have about 93% capacity. At 3 GPM or 2.5, that's where we get 100% of our capacity of our resin. Now we understand where reserve capacity comes from based on flow rate. And one of the traditional rules of thumb in the water softening industry and residential applications is a 30% reserve capacity. That seems like a lot until you understand 3/4 inch plumbing moves a heck of a lot more water than 5 gallons per minute. I've got a busy household with 6 people in it. It is not unusual to have 2 showers, a dishwasher, and a washing machine all running at the same time in my house. That's far greater than 5 GPM. But if we extend this line out down to here at 70%, up to 11 GPM approximately, now we understand where that 30% reserve capacity comes in. It helps us prevent overrunning the softener with flow rate. But if we design our system properly for the customer, we can stay up in here without having to adjust. One simple graph gives us a lot of reasoning why decisions were made in the industry. Here's their regeneration level. This resin's quite a bit different than that first chart we looked at. That's just a general generic chart covering every resin ever made, just kind of boiled down generic. But here you've got pounds of salt per cubic foot, our kilograms capacity. At 10 cubic feet on this particular resin, we're looking at 31,000 grains recovered. So resin selection may impact your design as well. So know your products you're using. It will be able to, when you get your head around all this stuff, you'll be able to tweak your designs. There is differentiation between resins and their kinetics, their flow kinetics. That's why resin manufacturers talk about this stuff all the time. There is differentiation here. At 3 pounds, this version of resin is somewhere closer to 16 or 17,000 grains. So just selecting a slightly different resin, I've got a couple more thousand grains of capacity. Know the products you're using, they'll impact your design. But this was about flow rate. We want to make sure that if we're using that 5 GPM rule of thumb, we're going to want to use a 10% minimum reserve capacity. Why? Because in reality, at 5 GPM, we're really only going to have about a 3% reserve capacity because of flow. This gets really, really technical the deeper we go down these rabbit holes. So just understand flow impacts capacity as well. The faster you push water through a resin, the less time it has to exchange, and you lose capacity because of it. So now we're talking about the hydraulics of the situation, the installation envelope we're putting our softener in, our system we're putting in. We understand how much resin is required. We understand starting to understand the impact of flow on that. So what happens when we're outside the flow restraints of our resin? What we're going to have to do? Well, plumbing size of the equipment we're going to treat or of the building determines peak flow possible. This is worst case scenario for that building. Hopefully that building was designed by a plumbing engineer who understands the equipment demands and sized it properly. Not always the case. Inlet plumbing size for the whole house is going to determine the size of the valve we need, right? But this is also based on the customer's needs. Do they need whole house softening, or do they just need hot side? Hot side is going to be the inlet to the water heater. And this is typically done in commercial applications because hot side is where all the real big financial gains are made from softening. Whereas in a residential application, it's about the overall experience and preventing scale buildup. There are commercial cases for doing whole house softening as well. It just tends to have the best economic impact on the hot side of things. The plumbing sets the peak flow of the building, whether it's residential or commercial. There may be pre-treatment of other applications that will be based on whatever you're trying to treat for whatever commercial business or the residence, depending on the water quality or depending upon the desired outcome of that water. Softening may be only one small piece of a treatment train. Okay, so this is one thing. In residential treatment, A softener tends to be a standalone item. You may have a carbon filter here or there, but it's really going to be predicated on water chemistry, right? Water determines the train. We're only really focusing on cation exchange in this discussion. Now, with commercial hours of operation, this will dictate whether or not you use single tanks or duplex tanks or alternating systems. We're not even going to get into networking system design at this point in time. Why? Too many rabbit holes to move. So hours of operation, if they need 24-hour soft water, we're going to go with a duplex in this scenario if we're going to do that. We're not. Most clay cases, it's going to be a single tank, and that's where we're standing. So you may be approximating a lot of this information, but if you get the pipe size, hardness, and whether they want it hot or cold, you've got a great number of these factors buttoned up. Now, we need to understand what flow rates pipes can handle at different pressures, okay? Run into pressure drop issues all the time. Just dealt with a case where a guy, sized a system that could do 60 GPM supposedly in a car wash, and they were getting no pressure out of their nozzles with 15 3/4-inch lines. Well, a 3/4-inch line can move between 8 and 28 GPM. Well, let's take if he's running at 60 PSI. Well, 20 GPM times 15 is 400. Oh, wait, I'm sorry, I can't do math this morning. 300 gallons per minute. Well, he's got a valve on that system that can only do 60, pushing way too much water through that resin. He's wondering why he was getting pressure drop. The system couldn't handle peak flow of all the hoses hooked up to the system. And that was probably on a 2-inch valve. That valve is probably able to handle something in this range of flow down in here. So understanding your flow demands is critical to getting this right in sizing the valve. So the system so far, we've got we're going to use 10 pounds of salt per cubic foot for the remainder of this. We've got a 1 cubic foot softener on this system so far at 5 GPM per cubic foot. We have a peak flow rate of 5 GPM here. So the minimum requirements for the residential system is 1 cubic foot of resin with a 3/4-inch valve that can flow 5 GPM. That's a slam dunk. 3/4-inch valve that can do 5 GPM. I can handle that all the way down to 10 PSI. No issues. Now for 10 pounds of salt in the commercial application, I'm going to select 5 GPM per cubic foot in the first scenario with a 2 cubic foot softener that can handle that. I can only handle 10 GPM. But with a 4 cubic foot softener, I can handle 20 GPM without a significant loss of capacity. So minimum requirement here, because in a commercial application only needing 10 GPM is kind of unheard of. I'm just going to step up to the larger one here at 20 GPM and say, oh, I'm going to need a 4 cubic foot resin tank and a 1-inch valve that can flow a minimum of 20 gallons per minute. Let's take a look at our chart. 1-inch valve, 20 gallons per minute. Yeah, on a 1-inch line, I can meet or exceed that flow rate. Okay, it's critical to understand here what a valve can flow is not what the resin can flow. Okay, that's one of the biggest mistakes in treatment, is not understanding that difference. Whatever we put in the tank determines the flow rate we can put through it. We're manufacturing a valve to meet the needs of whatever our dealer network wants to put in a tank, not just resin. Okay. Now, the media itself in the tank determines the design of the system for flow. Okay, makes choosing a valve a lot easier though. So when sized on hardness alone, the resin amount determines the peak flow we can put through that softener, period. Or we're going to lose our kinetics, or we're not going to be very efficient on water or salt use. So what do we do if we have a greater flow demand than capacity? I kept, just shrunk down the information in the previous slides here. So what in this home, what if I have a 10 GPM is required? All using the 5 GPM per cubic foot, I can use a 2 cubic foot of resin if I want to get the most effective use out of my capacity in salt. I could let this fly with a 1 cubic foot and use a 30% reserve capacity and let my customer run water through it far faster than that 5 GPM, right? But I'm losing capacity. So if I want to maintain that capacity and that ability to limit the amount of salt they use long term, I'm going to want to use this design factor to get this well. Residential work quite often just says, you know what, we're not going to do this to limit the expense on it. You can see why a lot of the system design out there isn't really focused on the hard technical stuff other than, making sure we can be competitive price-wise, because your customers aren't sitting through this presentation. That's part of this, and people aren't taking the time to explain it. So in this scenario, the valve remains the same, but the tank and the resin amount changes if we want to keep that 5 GPM per cubic foot in our performance of our resin where it is, because we bought that resin for a purpose. In the commercial case, what if I need 50 GPM? While using 5 GPM per cubic feet at 50 GPM, that equals 10 cubic feet of resin to meet the flow demand. While that has changed this design based on flow rate, it changes the valve, tank, and resin amount, and this determines a minimum of 1.25 inch valve. Flow may be more of a critical factor than capacity, especially in commercial applications. Commercial applications, a lot of times, the flow is going to be more important than the overall capacity of the resin. Okay, we need to be able to supply businesses with the water they're going to use. So let's take a look at that 1.25 inch valve. 50 GPM, I can go down as low as 20 PSI on an 1.25 inch pipe. This is the pipe by itself. This isn't necessarily what the valve can do either, but this is the flow demand that pipe can carry. This is our target. A 1 inch line is way too small. We got to be running up at 100 PSI to get that 50 GPM. So we need to be here with the plumbing size in the building. Well, guess what? If our customer's equipment requires 50 GPM and they've only got 1 inch lines here, there may be some interesting plumbing work for that customer in the future. So understand, hydraulic envelope is critical to success in water treatment. So capacity versus flow. Here's that chart again. So we must determine what the limiting factor of our design is. Is it flow demand or is it capacity? And that's going to be determined by your customer's needs, wants, desires, and the water chemistry involved. Okay, you can adjust capacity somewhat by using more salt, but then that means operating the system becomes more expensive from a salt sense. If we push too much water through the softener, we lose capacity. Is that capacity loss acceptable? In the residential market, we determine that pretty much is. In a commercial market, that may not be acceptable. Okay, so 50 gallons per minute, 5 GPM, that's 10 cubic feet of resin. At 9 GPM, we have 80% of our capacity. So that's an interesting factor, that if they pull more water than the 50 GPM, we're going to lose some capacity. That's why we always like to size things for the hard cut of their range and performance. They perform best. So 27,000 grains at 50,000 grains per day, 4.5 days between regenerations. That equals 67 regens a year. Well, what happens if we run it at that 9 GPM rate at that same 10 cubic foot size? Well, we lose 20%. Now we regenerate every 4.3 days. That's 85 regens a year. That's a lot more salt and a lot more water because we push more water through the unit. How your customers use their equipment is going to impact the cost of using it. Water softening is pay per play. For every gallon you run through it, it costs you X amount of dollars. The faster you run that water through your softener, the more it costs. That's what it boils down to. So we're going to be balancing all these factors. And what happens in this, in system design, is you push one lever, something else changes. So it's sort of like balancing out a graphic equalizer board in music, where you push one thing, everything else moves with it. Same thing happens in water treatment. Understand the impact of higher flows on your system and its cost. In a residence, we're not really concerned about this. We're concerned, not nearly as concerned about this as in a commercial application. This is a significant increase in cost, 20% more. Now, brining decisions and their impact. So this is just a real simple case we came up with. It's a simple scenario. A softener that can last 16 days between regenerations, 32,000 grains. That's rebrining at 15 pounds or 18 pounds of salt here. That's, at 10 grains, that's every 16 days it's going to regenerate. It's going to do that 2 times in a month. That's 36 pounds of salt in a month. Okay, but it's a lot less water. Okay, only 2 regens, not a whole lot of water, but a lot of salt. Scenario 2 is we drop down to that 15,000 number at 3 pounds in 200 grains. That's going to happen in 7.5 days. So we're going to have 4 regenerations a month in that scenario. At 3 pounds, only 12 pounds of salt are being used. But I've also doubled the amount of, at least doubled the amount of water we're going to use. Quadrupled it almost in this scenario. So depending on water cost and salt cost, that's where regeneration, you're going to pick that on that curve. What is the most cost effective? That's why that 9 to 10 pound range tends to be the best balance between salt use and water use for cost. Okay, I pay for water and sewer. I regenerated 9 pounds of salt. I'd rather use a little more salt, regenerate less frequently because I'm paying for my water. If I'm on a well, I may go down to 3 pounds of salt. Why? Because my water's coming out of the ground. I'm not paying for it. I'm just paying for the treatment of it. This makes a lot of sense to me, but I'm going to have bigger equipment. Flow demands. Lots going on here. Substantially less salt is consumed here. So if we look at the softening exchange process, this is just a quick look at chemistry. Okay. What we typically deal with in hardness is calcium and magnesium. These 2 guys right here. Everything bigger on the periodic table, farther down the chart on the periodic table when it comes to cations, is more tightly held by a cation exchange resin. It'll be removed first, preferentially to these. Why? Stronger magnets, bigger shape, fits tighter into the lock and key sort of design of the resin. Harder to get off because of that size, because we got to squeeze this guy in to push it off. So if you're dealing with high levels of iron, aluminum, barium in the water, things like that, any other really weird exotic stuff in the water, that is going to require more salt to get it off the resin. We need more helpers to pick it up, more charge equivalents to get rid of this. I need 3 sodiums to get rid of 1 aluminum. I need 2 sodiums to get rid of 1 calcium. And I may need like 1.2 sodiums to help push this manganese off. Okay, so water chemistry will impact brining as well. This is just, let you know that that reality exists as well. We draw that line for iron treatment with ion exchange at 5 ppm. If you've got greater than 5 ppm, I suggest in residential applications, definitely use an iron treatment system, or think about exploring specialized cation exchange resins designed around managing iron issues. There's ones out there that supposedly can handle up to 22 parts per million of iron per cubic foot of resin, no issues, and are more efficient at doing it. But resins themselves is another rabbit hole. Now, injector sizing. How do we size the injector for the valve for this scenario? How do we pick the right one? We have lots of injectors based on valve family and size. The injector brine system here, and we have lots of different flow controls here. What we're interested in doing is making sure we get the right injector for the resin we've selected. Remember, this is all about what we're putting in the tank, not about the valve. All right, the valve just sets the scenario for success. So when we get regenerate flow suggested here, we're going to take the middle of the road scenario. Suggested resin flow is between 0.25 and 0.50 GPM per square foot of resin. I like to average that out and get a 0.75. Why? That helps mitigate pressure changes in the building during regeneration. So get the information right from your manufacturer. So cubic feet of resin times the resin manufacturer's recommended regenerate flow rate equals the total injector flow. Okay, and the situation prior, we had 2 cubic feet of resin in the residential case at 0.375 gallons per minute. Average rate for that resin equals 0.7 GPM total flow rate of the brine coming out of the tank mixed with the water coming into the injector. The residential case at 10 cubic feet, 0.375 times the flow rate, the cubic feet of resin, I get 3.75 GPM total flow rate. Note, this is specific to the resin manufacturer, not to the valve. You're selecting this for the resin. So, and this is operating PSI, not static PSI. Okay? That means when we're flowing water, what's the pressure going in? Big fan of pressure gauges before and after systems, so I can understand what's going on. Seldom done in residential cases. Maybe it's done when you're checking things out and you're setting things up, but normally pressure gauges don't exist in homes. Okay? Businesses, good idea to put these in before and after. Great troubleshooting. Injector charts are for total flow. You're going to get that from us in our manuals for the valve. Equals injector size. So for the residential case, we're looking at the 1600 injectors typically, or the 1610 at 60 PSI. I'm going to assume we've got that there. I need to meet that 0.75 flow. I'm going to go across, and let's say this was 0.75. I'm going to go up to the next one up to make sure I can compensate for pressure drop, right? Here's 0.78. I drop down to 40 PSI, I'm down to 0.68. If I go up, I'm at 0.9. That's going to affect my brine ratio a little bit. So here, the residential case, we're going to have a number 1 injector. If depending on the valve, we may use a number 0 injector, depending on the valve and the injector system it's using. Know the valve you're using. For the commercial case, I needed 3.75. At 60 PSI on the 1700 injector, I'm going to need a 3.88 gallon per minute injector, and that's the number 4C. I've just picked the injector for the valve. Okay, we've got our brining set. We know which injector we're going to use for our valve. We know which injector system we're going to use. We know the flow rate of the valve we need. Now, backwashing. We got to do the dishes. We got to clean up the resin. Why? Dirt coating the resin prevents exchange sites from having access to the water. It's literally coating that resin with sludge that prevents it from interacting with the water. Okay? Cation resins typically need a 50 to 75% bed expansion. Pick the median. I like to do 60%. To manage seasonable changes in water temperature. Now, 50 to 75% bed expansion is the volume of the water in the space in between the resin itself. So we mean bed expansion. We mean just expanding the resin itself by 50 to 75%. So I have a cubic foot of resin. I only need about a 25% more space above it to get that 50% expansion because we're moving everything 50% apart distance-wise. There's some interesting math there. But this reclassifies the bed, forces the resin off. The classification is important because it puts the finest bits at the top of the tank, which is the best exchange kinetics, and the worst exchange kinetics at the bottom of the tank, where we're going to use our reserve capacity. All right, we want to backwash for at least 5 minutes until the water is clear with 50% bed expansion. Colder the water, the more efficient the backwash. The warmer the water, the less efficient the backwash. So in warmer climates, you're going to be backwashing more. You can see here backwash flow rate required at different temperatures. I like to use the 60-degree mark because it's halfway in between the two. Average groundwater temperatures in North America, 55 to 58 degrees, comes into a building, warms up a little bit. All right. So I'm looking at between 50 and 75%. I want to shoot for the median right in here. I'm looking at a 5 GPM flow rate that's required to get my 60% expansion on this resin. That's going to be the drain line flow control range I want to shoot for. I need to get that per square foot of resin. So this is where I need to do a little more math on the square feet of a bed of a tank. So we need the square feet of the tank bed area times the resin manufacturer's backwash flow rate in gallons per minute per square foot of resin. This is based on the size of the column of the tank, how that flat surface at the top, not the overall depth of the bed, because we're lifting it up, okay? This is equal to backwash flow rate of your system. So if you take the diameter in inches, you square it, and you multiply it by this factor. I left all the crazy units off this just for simplicity. This equals the square footage of the tank bed in area. So what does that mean? A 10-inch tank is going to have a 0.55 square foot surface area, regardless of height of tank. Okay? And that's going to be a 6 gallon per minute per square foot backwash flow rate from the manufacturer. I'm going to take that and take 0.55 square feet times GPM per square feet. That's going to give me 3.3 GPM in my backwash flow rate. This is now the size of the flow control I need to select minimum. So I need a minimum of 3.0, or 3.3 GPM backwash flow control. Now, in the case of a 10 cubic foot scenario, I need a 24-inch tank to hold that resin. Lots of charts on there on tank size and how much resin they hold. Just go to those charts. You'll pick your tank size off of that. Thank goodness for engineers, they do that math for us. This ends up in that same calculation to 3.14 square feet of surface area at 60 degrees F. Doing the same calculation, 0.34 times 10 3.14 times 6 gallons per minute per foot squared equals 18.8 or 19 gallon per minute backwash flow rate. So we need a minimum of 19 gallons per minute backwash flow control for this valve. Adding components to the valve here. Cleaning the resin is critical to long-term success. Do this well. Don't chintz on this. So here's all our backwash flow controls. Well, residential, I don't have a 3.3. I have a 3.5. I'm going to pick the 3.5. In the commercial, I don't have a 19. I'm going to pick a 20. All right. I've selected my flow washers there. This is a generic chart off of backwash flow control sizing per tank. Notice that for our resin manufacturer requires almost 5 GPM higher than this generic chart. Go to your OEM resins manufacturer spec sheet. Using generic charts will lead you to some failure. Okay? Depending upon the resin, it might be fine for your resin. Understand the reality of the products you're using. So we want to have 2 bed volumes to backwash a tank properly. Okay? So that means we are going to run a minimum of 14.5 gallons per cubic foot of water through it. 10 cubic feet times 7.5 gallons equals 4 minute minimum backwash at 20 GPM drain line flow control. That's going to get our resin clean and get it set up for operation. So we're going to put this all together. Residential. Need 1 cubic foot to meet the flow demand significantly. Flow demand significantly exceeds daily capacity here. We're going to require a 10 by 40 inch tank to put that cubic foot in, a 3/4 inch valve to meet that flow rate. That means we can use a 5600, a 5800, or a 2510 valve that all meet the flow requirements of the tank design and resin. We can use, depending on the valve, a 1600 injector with a number 1 injector, a 1610 injector with a number 0 injector, depending on valve you chose, and a drain line flow control of 3.5 GPM. So you're going to select one of these valves, understand the injector system that's on it, select the part number for the injector and the drain line flow control. In the commercial case with 10 cubic feet of resin, we're going to use a 24 by 72 inch tank with a minimum of 1.25 inch valve to flow at 50 GPM. Well, our 1.25 inch valve doesn't meet the 50 GPM flow requirement. The valve we have is 1.5 inch 2815 valve with a 1700 injector with a number 4C injector there with a 20 gallon per minute drain line flow control. Tank, valve, and resin are properly sized for a happy customer now. We've eliminated a lot of the simple, this is just a simple design scenario as well. Lots of information here. So these systems were designed on very general information. The better you understand your customer's needs, the more you can adjust and squeeze cost out of the system. Commercial systems will require more discovery work in order to optimize their system. pressure gauges with follower needles, flow meters, that type of system, type of information, gathering peak flow data off of existing softeners. Get that data. It'll help you tweak your design. Not all customers' supplied data is accurate. Make sure you're getting real world information, not necessarily what your customer told you to. Very difficult to go back and point the finger at the customer and say, you gave me bad information. Not a good place as a business to be in. When in doubt, size for worst case scenario. Complex design may require network systems in multiple tanks. Water chemistry may complicate sizing as well. Dirt load impacts performance, so pre-filtration may be required to maintain that softener's efficiency. Water versus salt cost inefficiencies will impact commercial design. Commercial design is getting the result as cheaply and as effectively as possible. Why? Service costs also play a role there as well. High-cost water markets will affect system design and programming of valves for water efficiency on municipal systems. Be aware of installation envelope. Doors, low ceilings, utilities, present or not, can a drain handle a backwash flow, etc. Those factors matter because we're putting this into a building that already exists. Beware of local water treatment regulations like brine restrictions that limit the amount of brine you can use. Waukesha, Wisconsin, lots of counties and towns in California are brine restricted. You're limited to the 3 pounds of salt or exchange tanks only. Programming and reserve capacity was not applied in this exercise. So you need to factor that into your design as well if you wish to do so. So these are some simple exercises in calculating size, lots of derivations from here, lots of ways to skin the cat. So what's fun about water treatment. So training requests, you know where we're at. Let's get on to questions. I want to go ahead and open the lines and let people ask away. I know you have a question, Sam. Can you go ahead and ask that one? I know you raised your hand earlier. I missed it. You were scrolled down.
Yeah, no problem. I was just thinking that it'd be really nice if we had some type of software or an app where you could just input all the information and it could give you, scenarios or options to put a system together.
You know what? They do exist, but they're done at the resin manufacturers have that software. But they're dealing with really large scale systems. They will talk you through it. But there are calculators out there that do some of this work, but they're running through exactly what we talked about today. They are not factoring in, most of them don't factor in water chemistry factors either, or water temperature as well.
Yeah.
So this is where the devil's in the details, and this is where individual companies differentiate themselves from other companies, is understanding the details here. In just presenting this today, thinking about this as I was going through it, this has led me to just 6 other presentations I need to construct.
Right.
So there's a lot here depending on how far you want to go down the rabbit hole. And I mean, we didn't even discuss sodium's impact naturally occurring in your water supply, impact on design. We didn't discuss iron. We didn't discuss, aluminum, which is common as a flocculant in system design. So no twin system discussion, no dual alternating tanks, no NXT2 conversation here, and progressive flow. So you really need to get a little invasive into people's existence in order to understand how to treat their water for them. Most of the time in residential cases, we're focused on the price tag of this system more so than its capabilities. But in commercial applications, we're focused on its capabilities and its cost to that customer. And that's the discussion you have with commercial customers. Yeah, I wish somebody would do that sort of for the residential market. There are some players in the market that are doing it with water efficiency and salt efficiency, and they're designing systems both ways, depending on who's buying their system. Because if I've got my own private well, I don't care about how much water I'm using unless I suck that thing dry, right?
That's right.
I'm more concerned about how much salt I'm putting in there. But if I've got to put in a 4 cubic foot system for my home to use 3 pounds of salt, I might not want to spend that money up front. So this is about a balancing of those cost structures. And there's so many different ways you can skin that cat. You're gonna find that place you like to play. And that's what's good about water treatment, and it's what's tough about it.
Okay, thank you.
Mm-hmm. And if you want to go into those discussions and review your systems, I've done offline, reviews of people's design systems and things like that, just to let you know where your systems presently are playing and where we can find some efficiencies, either water-wise or salt-wise, that type of stuff.
Okay.
So we're happy to help you guys out with that. And we can reach out and tap some resin manufacturers as well if you really need to talk to those guys about their design systems. There are a lot of good people with those companies, and they want to help you move their product as well. They make resin, we make valves and tanks. Sometimes we don't play nice together.
Question, Dave.
Yes.
And this may not have anything to do with softeners, but it does affect valves. We're seeing a lot of homes going to 1-inch water lines and coming to the house.
Correct.
Why are they doing that? I mean, you showed there real clearly 60 PSI, a 3/4 inch line will give you all the water flow you probably could ever use in most homes. So what's driving that? Is it, I assume the McMansions might need more, but just a standard home, 3-bedroom type of thing.
It's because of they aren't building those homes, those factors, those numbers in based on the number of people that live there. They're doing it based on the number of devices in the home, with the possibility of all those devices being turned on at once. It very seldom happens, but as a design engineer for a home, you have 2 choices. You either target the middle of the road, the average in between the extremes, and hope it works out, or you take worst case scenario. Most of the time, engineers will err on the side of worst case scenario. So they add up all the faucets, all the toilets, all the showers, the washing machines, the dishwashers, and go, if everything was on at once, what flow do I need?
Okay, that makes sense from an engineer's viewpoint. I don't know how you turn on every faucet, every shower, dishwasher, washing machine, and flush all the toilets at once.
In my house, that actually happens.
Okay.
My son had his buddies over for Dungeons and Dragons the other night. Okay. My wife was in the shower. My daughter was in the shower. She had run a load of laundry before going in. The dishwasher was running because I ran it. And I had another kid upstairs in the bathroom flushing the toilet. All that stuff was going on at once.
Okay.
And it's really about the design of the home and the potential for use. And that's where we run into some problems on the low flow side. You got to be able to handle the low flow side as well.
Why has that changed? I mean, the homes haven't changed, people haven't changed, but they ran into problems with that flow rate? The 3/4 inch?
Well, because the softener can only handle 5 GPM, right?
Right.
So basically 5 to 9, gallons per minute. So we were restricting flow and having pressure drop. The last thing anybody wants to experience in a home is pressure drop in their shower.
Right.
Okay. It's that intangible humanness that we have to design in for. It's the same thing with some water softeners. It's about the feel of the water. There's a lot of economic benefits, but when it comes down to it, it's about how my water makes me feel, gets me clean, makes my hair look better, keeps my clothes looking nicer. Those real human interactions factor into a lot of the mechanical design process.
Yeah, I understand. I'm kind of looking at the softener. If you go to a 1-inch valve, you still, say the 5810, and you still have a 1 cubic foot softener because that's the capacity you need. You're not really improving the flow rate, are you? Because the resin's restricting the flow versus the valve. The valve can do a lot more. The resin restricts it. You can run a 3-inch valve.
The resin can do more than that 5 GPM, except it's all about what happens at the molecular level when you're exchanging a calcium for a sodium or 2 sodiums, okay? It's how fast that reaction can take place. At 9 or 10 GPM, we lose 30% of our ability to do that. We're just not able to get the contact with the resin long enough to get all the hardness blowing by in the stream.
Okay, so you're losing capacity. You're not blowing by so fast that you lose softening.
Yes, you just lose part of it. And you just have to factor that in. So yeah, I could factor in my softener to flow at 10 GPM per cubic foot, but instead of 90%, 100% capacity, I'm going to get 70% capacity. And I haven't even started playing with my brine yet.
Right.
So the faster you flow your water, it's going to impact your brining as well. So there's a lot. It's that graphic equalizer board again. The more you push up, the more you change. It changes other things in the system.
Okay. Another quick question on hydraulics.
Yeah.
And you talked about pipe size. Do the hydraulics in the house affect that? A 3-story house versus a 2-story, the rise on the backside. Is that something that comes into play, or is that just overall hydraulics in the system? What kind of pressure you get at the 3rd story in the shower, you got to calculate that in to calculate pipe size going to it.
At median pressures, 40 to 60 PSI, not really a big issue.
Okay.
Dealing with buildings bigger than a story, it becomes impactful to the experience of the water pressure coming out. On the performance of the softener, no.
Okay. I didn't think it affected the softener.
Yeah, it slows down the flow rate through it, actually, because you got back pressure on it. So it actually will improve performance technically, but you're losing flow. Now, in a high-rise apartment building, yeah, and there's quite often booster pumps either prior to the softener, which is not necessarily a good deal, or on each floor pushing pressure for higher floors. That does happen, but that will impact an RO system significantly if you're trying to pump RO water upstairs. If you got to go more than a story, from your basement to your sink underneath, that's really not a huge change in elevation. It does have some impact, but if you're going a full 13 feet in the story, that will impact over time.
Okay.
Fun discussion. Yeah, this was simple cases, and this is a really, really in-depth topic. That's why we quite often see guys that just know in, out, and drain in water treatment, is they don't want to go through and dig into the details here. They rely on people like us or our distributors to size things appropriately. Well, when somebody misses, they tend to miss big. And that's the problem with it. And that becomes real expensive for the guy on the street. If we miss big, he takes it on the chin and tearing equipment out, buying new equipment and putting it back. And then there's that finger pointing session. So
right, I can see that, particularly in commercial applications, much more critical. I guess what hits the consumer, homeowner, they end up using more salt than they thought they were going to do, or more water than what they expected because of missizing. And they didn't know how much salt they used before they put it in. So it's hard for them to say, wow, this is using a lot more than I thought it would, because it's always used. I had to put 2 bags every day since I had this thing in there.
Yeah.
Okay.
Yeah. Then regenerating at 15 or 18 pounds per cubic foot. Yeah, you're going to get all your capacity. Well, yeah, but your salt expense is going to be high. Your water cost from running the softener is going to be minimized. But that all depends on where you live.
And very few people know what their cost per gallon of water is, I would think. I mean, I have no clue.
Yeah, well, what I know is if I change a setting on it, I see my bill changes. And there is going to be, going forward into the future, there's going to be a lot of regulations around brine at some point.
Yeah. And is that brine in general or salt brine?
Salt brine in general.
Okay. Versus potassium brine.
Yeah, until that becomes prevalent, and then that becomes the issue. Because pollution is all about dilution. There's an old adage in chemistry: the solution to pollution is dilution. You dilute something enough, you don't have problems with it. Until you do. So, there's going to be a lot of interesting stuff coming out of this, and there's even some people doing some interesting things with recovering rare earth metals and significantly valuable metals from commercial brining waste streams and desalinization plants to offer a profit stream out of the waste stream of softening. So there's going to be a lot of that circularity discussion. The next 100 years, I guarantee circularity and extracting profit out of the waste stream is going to be the key to OEMs going forward. And the people that do that best are going to be the company that succeed.
Yeah. Again, that's probably more commercial. I doubt if a homeowner is going to try and pull profit out of his waste stream, but you never know.
Well, there's the economy of scale. Where that's going to happen is not at the homeowner level, but at the wastewater treatment plant.
Yeah.
They're already pulling trace amounts of gold and platinum out of waste. There's some interesting stuff on that scale. I was just reading that this week. So.
And one other quick question on testing your water. Obviously, I know how you can do your get the city reports, and you can test for hardness fairly easy. If you're looking for iron test, is that something you're probably going to have to send to a lab, or is that something you can do, average homeowner can do at home?
You can do a iron test. An average homeowner can do at home, but there's a sort of a 3-step process there to determine between dissolved iron and particulate iron. Okay. That way you understand the particulate load you're dealing with, and then the chemistry load, because the removal of iron from water has some impact on pH of the water, and that has impact on everything downstream. So
if you're doing it with the air injection or something like that, if it's pulling out via your softener, does it affect your pH if you've got it, 3 parts per million and your softener's pulling the iron out?
Well, the
ion exchange?
If it's directly exchanging iron out as we think it's behaving, yes. But resins have a lot of different functional groups that contain oxygens. Okay, that iron get bound to the resin in such a way that it may actually break off those oxygens off of functional groups and precipitate out as rust, iron 3 oxide. So there are cases where the iron becomes so tightly bound to the resin that you can't get it off. So there's a lot of interesting chemistry going on there. And that's one of those discussions I'd love to have in a very brief 15-minute discussion. You can talk about that just looking at, the exchange sites, and you can understand why that happens. But it's really a matter of how big the individual cation is in solution and how well it fits into that space on the resin. Because all the metals that we're removing, typically water removed from the water, are +2.
Right.
So what we're doing is taking one out of the water, a calcium or an iron, and giving out 2 sodiums. That means on the structure of the molecule, you have to be within 2 exchange sites to remove it, 2 sodiums. And depending on how you fit in that space determines how tightly held you are. And the bigger the charge and the more hands you have reaching out to the molecule, the tighter you're held before you can be exchanged off.
Okay. And we have another question in the Q&A. Have you looked at that one? What should I do in cases of low service flow and a high hardness in water? Should I go to multiple systems?
High hardness in low service flow. I would suggest in that scenario, you either want to keep a bare minimum of about 2 to 3 GPM flow rate through that system. Okay, so I would either consider possibly either a booster pump in front of that to make sure I've got the flow. But if I've got low flow but really high hardness, I might think about a twin system, because I want to keep the capacity and the size of my system small because the investment in equipment, and then just switch tanks and keep my flow the same without having to go to much larger pieces of equipment, which drops my flow rate too low where I get channeling through the bed. That's the other end of this discussion as well. So I would suggest either a boost pump in front of it, increase the well pump pressure if you can. If not, I would go to a twin alternating system to make sure my flow capacity matches. But slow flow is not necessarily a bad thing with ion exchange resins until it's too slow. You get better capacity out of it. You actually get at about 2 gallons per minute of flow, you actually get more capacity out of the resin. So it's a real interesting dynamic.
And you're saying with low flow, you're talking versus no flow. When all the water's shoved off, that's not causing any issue. It's when you're getting flow continually at a half gallon or 1 gallon, you'll have issues in your softener.
Yeah, because the water doesn't compact the resin as it's flowing. It sort of slips between the grains and slides out. And that's what low flow is bad. So that's where progressive flow systems come into play. Is you're either going to cram too much water through a tank or not enough. If you have too much capacity to meet the flow, and you have only one, like let's say manufacturing line, you don't want 6 tanks, right? Because 6 tanks, that's too low a flow for all 6 of them. But it's fine for 1. But you start bringing on manufacturing lines, we're going to go add 2 minutes of flow and then back it down. So yeah, variable flow situations adds another layer of complexity here as well. So understanding the environment of that customer is putting a piece of equipment in is critical for being successful. If you know you've got low pressures to begin with and lower flows, understand what that flow is. If it's less than a gallon per minute, we need to improve the pressure situation. Or the other case scenario, which you probably aren't going to find a whole lot of these on the market, is a skinnier and taller tank. Decrease the surface area, but yet extend the column. And those don't exist in residential or commercial water treatment. Those exist in laboratories. So if you wanted to create a low flow softener, that's actually how you do it, is have a long, tall, skinny column, but it was narrow. Depending on flow demand, if you're dealing with that situation and overall water use, that's where some bowl softening may actually make sense. It all depends on overall water demand and cost threshold. Lots of levers here.
Okay. Well, we better let everybody go. We're an hour and 15 minutes into this, which has been a great session, at least from my viewpoint, and it looks like most people enjoyed it.
Thanks very much for attending, and we'll hopefully talk to you next Tuesday.